Hey everybody, this is a follow-up video for my VR64 project. This is the project where I made virtual reality goggles for the Commodore 64. In this video, I'm not actually going to be talking too much about the VR goggles, so I'll put a link to the original project below. But what I am talking about is the game Street Defender that was made for the VR64 and the input devices for this game. The game is available in floppy and cassette and of course download. But when I first made this game, you can rotate around and look down 4 different street corners and attack your enemy with 4 different attack modes. So, with the goggles on your head, you're not going to be able to see the controls very well. So I thought, well, we'll use the top 2 keys to rotate left and right and the 4 function keys for attack. And that worked really well. But I always wanted to be able to rotate the character in a more natural way, and I thought the best way to do that in an 80s fashion is to use the Atari driving controller. And this is the one that spins continuously. This came with the Indy 500 game for the Atari 2600, and so it plugs right into the 9-pin joystick port, and so I'll demo this working with a new version of Street Defender here. So I got the game loaded up, press the space bar and start the game. And let's see, I'll put up here so we can kind of see. As I rotate, you can see the views rotate. And rotate this way, you can see the views rotate. Go back to the enemies, let's kill some of these guys. So it actually ends up giving the game a little bit more of an analog feel. It's really, I think, is a good addition to the game. With the keys, people would typically just hit them twice to go to the next screen. This, you also have the effect of overshooting your enemies, and so that kind of adds another element to the game. So it's a really fun element to the game. I like it a lot, but it was a challenge, and it was, I did learn a lot implementing this. So now that I've demoed this, I'll talk about how it works and some of the challenges I had for those that are interested. So I wanted to use this controller because it is the one that spins continuously around with no stops. The tennis controller does have stops in it, and it is really just a potentiometer, so it's a resistance value that's inputted in. I wasn't sure exactly how this worked, but I kind of had suspicions, and it turned out to be pretty much that way. So for the regular joystick port, you pick a location in memory, and you get a byte out, and the different bits in the byte define what's going on. So if the first bit is 0, then up is pushed. Second bit is down, third bit's left, right, and then fire. So that, really, you get a byte out of this memory location. You can pull the bits out and figure out what's going on with the joystick. I knew this would be different. So what I did is when I was able to, I plugged it in and read this memory location, I started getting funny values. 127, 125, 124, 126. They were not in sequential order. And what I realized is it's really just these last 2 bits, the up and down, that are changing as this rotates. And so it only has 4 states in it. It rotates, and that's with 90 degrees of the rotation, so it repeats 4 times. And what it does here is it's using a quadrature output or a gray code where only 1 bit changes at a time. So you can see here if it's 1, 1, it goes to 0, 1, and then it goes 0, 0, and then 1, 0. And this is not how binary would normally count, and that's why you get this weird output. So a funny thing happened. I actually wrote this first and then realized I put it in pure sequential order, not this funny order. So I X'd it out. But you can see here actually why they do this funny sequence here. If they did it in a more natural arrangement, 127, 126, 125, 124, the bit patterns would be 1, 1, 1, 0, 0, 1, and 0, 0. And you can see here going from 1 0 to 0 1, both bits are changing. And so if you were between these two states and it was fluttering between these two bit patterns, you could actually encode any of these positions and you wouldn't know where you are at all. Down here, because only one bit is changing at a time, if you're fluttering between two states, it's between two adjacent states, and it's that one bit that's changing. So that's why they do this instead of this pattern, so that you are always coding between two adjacent states. So I wrote a little demo program in BASIC that demonstrates this. Let's load up this directory. Go to this one, input sample. So it's a pretty simple program. It reads DR from memory, that memory location, the drive controller, clears the screen, prints DR, and then it sets bit 0 and bit 1 to the string 0. And then it does a bitwise test. If DR and 1, then B0 equals 1. If DR and 2, then bit 1 equals 1. So that's just trying to tease out those 1s and 0s for those first two bits, and then it prints the two bits and repeats. So let's run this. Alright, pretty simple. 127.11, and we'll go ahead and start rotating the controller. 125.01, 124.00, 126.10. What do you think next is? 127.11, and it just repeats. So it works just like we thought it did here. That's how this thing gets the whole rotational output. So in the assembler code, all I did was set up current and last readings and then compared the two, and if the new reading is different than the last one, then I could figure out if it was one value or another value. Then I either went clockwise or counterclockwise, and this worked really well, except when I first implemented it. You know, these old computers and games time a lot of things on the raster rate, and I had it reading this once per cycle. So it would do a lot of things when we were down in this border here, set up the new graphics and things for the next screen, and it would read this controller at that point. And what was happening is I was able to change two states by the time it got back here to read it again. And then, so we had the new state and we had the old state, and they wouldn't be next to each other. So we didn't know how we got there, whether we went clockwise or counterclockwise. So the software really wasn't working very well. What I was able to do is set up 3 different points on the screen where it ran this interrupt. It ran the reading of this controller, and it's been rock solid. And it actually worked so well that I would actually visually sometimes skip screens, so I wouldn't see the screens between one direction and the next direction. So I actually created a little buffer in the software, so it actually is forced to scan through all those screens, and that creates a much more natural look to it. So I thought this was a really fun project, interfacing an old Atari controller to a Commodore 64. This controller, again, didn't get much love back in the day, not a lot of games. So I will have a new version of the game available for download for those who own the system, or you want to try it with the 2 views on your own system. One point of warning, you might be able to see it here. I put a piece of blue tape on the front of this, and that is when the controller is at this 127.11, and so up and down are not pushed at that point. And even though this is plugged into joystick port 2, if it is in one of these other positions, it will interfere with the keyboard and cause it to do some funny things. So that is a idiosyncrasy of using a drive controller on a Commodore 64. Port 1 it really messes up with, and port 2 it's kind of a hidden mess up, and like some of the keys don't work and you get confused. All right, hope you guys enjoyed this. Thanks for checking it out. Talk to you later. Bye.